Hi, welcome to Sam's Maths Lectures. This is my first lecture on sort of set theory. It's going to be slightly more than just set theory. Okay, so when we talk about maths as a subject, there are sort of three big things that we have. We have sort of mathematical structures, so we've got groups, topological spaces, manifolds, sets, basically. Every structure, pretty much every structure has a set underlying it. Then we have functions between sets, whether they are homomorphisms, isomorphisms, whatever. We've got some form of function usually. And then using these structures and these functions, we construct proofs, sort of logical statements that follow from each other, and we use these to prove things and give us sort of useful insights about mathematical structures and also how they relate to the real world. So that's sort of three big things, and the idea of this course is to sort of address all of them. Predominantly sets, that's why it's called set theory and not set proof and function theory. So I'm going to start with some sort of basic mathematical notions of logic and how we prove things, and then I'm going to talk about set theory, axiomatic set theory, which is a rigorous system for sort of defining the properties of sets in such a way that we don't run into nasty paradoxes, which I'll sort of present later. And then, some basic stuff on functions and relations and whatever. Okay. So let's start with logic. Okay, so the most basic thing is a proposition, which is a statement, precisely formulated statement, which is either true or false. So one proposition could be, today is Wednesday. Okay, today could be Wednesday or it could not be Wednesday. It can't half be Wednesday. Okay, and it's not always true. It's not always false. Sometimes it is Wednesday. Sometimes it is not Wednesday. Okay, so that's what a proposition is. Proposition is either true or it is false. Okay, and then sometimes we introduce some form of variable, and so we can have a proposition of a variable, and you can think of this as a true or false valued function of a variable, in a loose sense of the word, and that's called a predicate. Okay, and so in maths we usually care more about predicates than just propositions, but we build propositions from predicates as well. Okay, so for example, x is prime is a proposition on x, and we sort of imply that x has to be a real number, or probably an integer, positive integer for this predicate. But you could say that actually we could take x to be the group of symmetries of a triangle, and x is not prime because x is not an integer, so it can't be prime. But we won't worry about that sort of thing right now. Okay, so propositions and predicates. Obviously, if we just have a set of isolated propositions and predicates, that's not very useful. We can't do anything with that. So we need a way to build things. Okay, so what we need is operators. So we start with unary operators. Unary operators, which take one proposition and return another proposition. Okay, so if we say P is our proposition, which can be either true or false, then we can draw this truth table. And so we have the identity of P, which is just going to be true or false, depending on what P is. Then we have the negation, neg P, like this. And so if P is true, the negation of P is false. And if P is false, the negation of P is true. Okay. Then we have tautology, TP. So a tautology is a statement that is always true, and so the tautology of P is always true. It's not very useful, but we may as well list it. And then the contradiction of P, a contradiction is always false. And these are the four possible operators. And the reason that there are four possible operators, we'll sort of see more about this later when we talk about functions, is that there are sort of two input values, and so we can then specify whether each input value gives us a true result or a false result, and that fully defines the function. And so we have sort of 2 to the 2 choices, which is 4. Okay. For binary operators, we take 2 propositions and we return a third. And so there are 4 possible combinations of binary operator, and so 16 total binary operators. We're not going to discuss all of them. So we've got P, we've got Q, false, false, true, true, false, true, false, and true. Okay. So which operators do we have here? So the first one is AND, so P and Q, or P sort of wedge Q. Okay, P and Q is true if and only if they are both true. Okay, so it is Wednesday and it is raining as a statement is only true if it is both Wednesday and raining, not just one of them, and certainly not if neither of them is true. Okay, then we have P or Q, and this one requires only one statement to be true. So this is a sort of inclusive OR. There are 2 types of OR generally in language. We can either have the inclusive OR, where it is Wednesday or it is raining, where it's Wednesday, it's raining, it's Wednesday and it's raining are allowed. Or we can have the exclusive OR, where it's Wednesday or it's raining, means it's Wednesday, it's raining, but not both. Okay. So we start with the inclusive OR because that's sort of more common, and so that's false and then true, true, true. And then we have the exclusive OR, sort of either or, so either P or Q, so only one of them. That's false, true, true, false. Okay. Then sort of the final useful thing, or not the final useful thing, of this class is NAND, so P, sometimes this is an up arrow, Q, and so basically this is just the negation of P and Q, and so that is going to be true, 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 or false. And so an important part of this is that any operator on any number of propositions can be built as a combination of NANDs. It's useful when you're building a circuit because it means you only need one type of logic gate. It's not so useful in maths because it generally makes things quite complicated unnecessarily. Okay, then we have implication. Okay, so P implies Q, or if P, then Q, in sort of more natural language. Okay, and so the truth table for this is true, true, false, true. Okay, and so why are there these 2 trues here? And so the sort of reason for that is if we took the statements, if we take the propositions, there are cars driving over London Bridge, okay, over Tower Bridge, then either there are or there are not, so that's a valid proposition. And London Bridge is, Tower Bridge, sorry, is down, then again, either it's down or it's up, okay. And if there are cars driving across it, then it is down, okay. That is a true statement because whenever there are cars driving across it, it must be down. But just because there aren't any cars driving across it does not mean it has to be up. You know, it could just be that there's no traffic at the moment. Okay, so that's what if P then Q sort of means, and that's quite useful. We'll sort of talk about that more in a second. Then we have the converse statement, which is P is implied by Q. And so this is just equivalent to Q implies P, which means that this one will be false and the rest will be true. And then finally we have P if and only if Q, or P is equivalent to Q. Okay, and so this is when both P implies Q and Q implies P. Okay, so that's going to be true, false, false, true. Okay, so let's talk more about what these mean. Okay, so P implies Q. Then we can see by sort of comparing the logic tables that this statement here is equivalent to not Q implies not P. Okay, so this is a sort of converse statement. So we can sort of flip this around, and we can see that by saying that if we stick in not P, not Q, and then their thing. Okay, so not P is going to be true, true, false, 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 no, sorry, true, false, true, false. Okay, and then not Q implies not P with brackets to help. Okay, so true implies true, true, false implies true, false, true implies, sorry, false implies true is true, true implies false is false, false implies false is true. Okay, and so these are exactly the same, and so they're equivalent because they're always sort of equal as statements. Okay, good. And so this is how we can sort of build up a proof by contradiction. So if we suppose that P implies Q, then we work out, say something satisfies not Q, then we show that that would cause P to be false. Okay, so that's how a proof by contradiction works. Then we also have using sort of any false value implies P is a tautology, so it's always true, whatever P is, as long as the left side is always false. And so this is called sort of ex falso quod libet, which means from falsehood comes anything. And so that's another useful idea in maths. We'll use that a bit. Okay. Then other useful statements is that if P implies Q and also Q implies P, then what that means is that this is equivalent to P is equivalent to Q. Okay, so we'll use this in proofs a lot because we'll sort of want to show two things are equivalent, so we'll show it forwards and then we'll show it backwards. Okay, and then some terms. P implies Q means that Q is necessary for P. Okay, because if Q is false, then P is false. So we must have Q being true for P to be true. If P is implied by Q, then Q is sufficient for P, because if Q is true, then P must be true. And then finally we have if both of them hold, so then we have that Q is necessary and sufficient for P. Or we could say that Q is true if and only if P. Okay, because if P is true, then Q is true, but also only if P is true is Q true. And sometimes we write this as IFF, for if and only if, as mathematical shorthand, and so they're equivalent. Okay. Finally, if we check the truth tables, we can see that not P or not Q is equivalent to not P and Q. And we can sort of see this by saying that not P or not Q means that at least one of P and Q is false, because at least one of not P and not Q is true, and that is equivalent to not both P and Q are true. Okay, and then we also have that not P and not Q is equivalent to not P or Q. Okay, so not P and not Q means that both of them must be false, so that both their negations are true, and that implies that not, well, that's the same as saying that neither P nor Q. Okay, and these are called DeMorgans Laws, and they're quite useful in sort of various aspects of set theory. Okay, then what else can we do? If we take a predicate, that doesn't have to just be of one variable. We could have predicates of multiple variables. So, for example, the predicate of, we could say, x, some predicate r on x and y, and then we write this colon here for is defined to be equivalent to x divides y. Okay, so that's a predicate of two variables, and a predicate of two variables we usually call a relation, and we actually usually replace the sort of letter in front and then the variables in brackets to some symbol between the letters, and so in this case that symbol is this sort of pipe for divides. Okay, so we usually write sort of x and then similar to y or whatever. Okay, so those are predicates. And then obviously if we have a predicate and we want to talk about it over multiple values of x, then we don't want to have to write out every value of x, because usually there is not, you can't do that. X is usually runs over too large a range in most applications, and so we use quantifiers. Okay, so quantifiers. So we have the sort of for all x, then p of x. This is a mathematical statement that says for every x, p of x is true. Okay, so that's what the for all means. So we could have, generally the sort of range that x runs over is specified contextually. We'll get more into that later. And then there exists x such that p of x, so for some x, p of x is true. And so this is equivalent to saying that not for every x, p of x is false. Okay, so for some x, p of x is true. Not necessarily all of them, but for at least one value of x. Okay, and then we also have the exist unique, but I'm not going to talk about that now. Okay, so those are quantifiers, and we'll use those to build up statements. Is that everything? Okay. Yeah. Okay, so what is a proof? Very loosely speaking, so we take these things called axioms, okay? Things we define to be true. So we will talk about these sort of axioms of set theory soon enough, and so those are things that we just say this is true, and anything for which any of these is not true is not a set, so we don't care about it, we're going to ignore it. For all of our sets, these axioms are true. And so they are sort of the building blocks of maths, in the same way that sort of fundamental laws of physics are the building blocks of physics, and so on. Okay, so axioms are things we define to be true, and so proofs are statements or propositions, or we'll say that a proof is a way to write a statement as equivalent to the axioms. Okay, so that's effectively what we do. Is equiv to the axioms. Okay, so I think I'm going to stop this one here, and then I will begin my next lecture with the first few axioms of axiomatic set theory. Okay, thanks for listening.